All right, today we're diving right to the absolute edge of engineering. We're exploring this tiny, microscopic battle of forces and fractures that, believe it or not, decides how we build pretty much everything, from jet engines to surgical implants. This is the science of the cut.
I mean, really think about that for a second. We've created these incredible superalloys that can handle the heat of a rocket engine, and titaniums that are both super strong and incredibly light. But how in the world do you take a solid chunk of that stuff and shape it with pinpoint precision?
Well, that's the secret right there. Every single cut, every hole drilled, every surface milled. It's actually a violent, high-stakes showdown between a cutting tool and the material it's shaping. And understanding that tiny battle is the key to, well, everything.
So to even have a chance of winning that microscopic war, engineers have this one central concept they always come back to: machinability. And getting a handle on this is fundamental to everything we're about to talk about.
You see, machinability isn't just about if you can cut something. It's about how well you can do it. Do you end up with a perfect, smooth surface? Does your expensive cutting tool actually survive the process? How much shear force does it take to make the cut? The answers to those questions, that's what defines a material's machinability. So how do scientists actually measure this stuff? Well, they basically become detectives, and they're always looking for 4 key clues. First, they study the chip morphology. That's just a fancy way of saying the shape of the metal shavings. Then they analyze tool wear, or how quickly the cutter breaks down. They measure the cutting forces, and finally, they inspect the quality of the final surface. Those 4 things tell the whole story.
Let's kick things off with that first piece of evidence, the chip. Now, you and I might just see it as scrap material to be thrown away, but to an engineer, it's a detailed report, written in metal, that tells them exactly what happened in that tiny moment of the cut.
This is honestly the best way to think about it. The chip's shape, its color, its thickness, all of it tells you if your process is stable and efficient, or if something is going horribly wrong. It's like an instant diagnosis.
So, a perfect cut produces this long, continuous, smooth ribbon of metal. That's a great sign. It means the process is stable. But when you're machining really tough materials like titanium, you often get these ugly, saw-toothed, segmented chips. And those are a huge red flag. They're basically screaming at you that there's extreme stress and heat, and you're probably getting a terrible finish and destroying your tool in the process. And that brings us perfectly to our second clue, the cutting tool itself. Because no matter how hard and tough that tool is, it is always in a brutal fight for its life.
The friction, the pressure, and the heat right there at the cutting edge are just immense. So by studying how a tool fails, we can actually optimize the entire process. In this world, tool wear isn't just a problem you try to avoid. It's critical data you have to analyze. And a tool can fail in a few different ways. There's flank wear, which is like a slow, grinding erosion. You've got coating fatigue, where the tool's protective shield starts to crack under all that pressure. Adhesion is a huge issue with gummy materials like aluminum, where bits of the metal literally weld themselves to the tool. And then, of course, there's just catastrophic breakage. Controlling these is the name of the game. Okay, so we get the problems, right? Bad chips, worn-out tools. The big question is, what can engineers actually do about it? Well, it turns out they have a whole bunch of levers they can pull to control the outcome of that microscopic battle. And what's crucial to understand here is that this is all a science of cause and effect. This table shows just a few of those levers. Notice how for magnesium alloys, changing the cutting speed is the single biggest factor influencing tool wear, or how using a special super hard coating can slash friction. Every single one of these is a variable that can be tuned for that perfect cut.
And if you want to see just how powerful one of these changes can be, this is a fantastic example. Look at the difference when machining stainless steel. If you cut it dry, you generate a ton of friction and heat. But what if you flood the cutting zone with liquid nitrogen? That's cryogenic milling. It completely changes the physics of the cut. Tool wear goes down, surface defects are reduced, and the final finish can be up to 71% better. It's a total game changer.
So, armed with all these principles, engineers can now tackle materials that were once considered pretty much impossible to machine. Let's look at a couple of really extreme examples. First up, Inconel 718. This is a nickel-based superalloy you'll find in jet engines and gas turbines because it stays unbelievably strong even when it's glowing red hot. Of course, that same property makes it an absolute nightmare to try and cut. So what's the solution? Well, it's brilliant. If you can't beat it, heat it. With thermal-assisted machining, you use a laser or a plasma torch to heat the material right in front of the cutting tool. This just softens it up enough to make it way easier to cut, and it can reduce the energy you need by as much as 30%.
Okay, next challenge, titanium alloys. We love these in aerospace and medicine for their amazing strength-to-weight ratio, but they are notoriously difficult to machine. They create those awful serrated chips we talked about and just chew through cutting tools.
Here, the solution is all in the geometry. Research has found that creating these incredibly small, wave-like textures on the surface of the cutting tool can have a huge effect. It can actually reduce the thickness of the chip as it's being formed and give you a much, much better surface finish. It's amazing how a microscopic change to the tool can have such a massive impact. And here's what's truly mind-blowing. These principles don't just apply to super tough metals. The science of the cut is universal. Engineers apply the exact same logic when they're machining wood for furniture, high-tech carbon fiber composites for aircraft, and even bone for orthopedic surgery.
That's because, fundamentally, the physics are the same. It doesn't matter if you're cutting steel or wood, you still have to manage how that chip forms, you have to maintain the sharpness of your tool, and you have to control the cutting forces to get a precise, clean result.
And that really brings us to our final thought. The quest for better materials is relentless. We are constantly designing stronger, lighter, more heat-resistant materials. And for every single new material we invent, we create a brand new machining challenge. The battle at that cutting edge is never really over. It just keeps evolving.